Okay, in our last video we ended with a function that was discontinuous. I want to talk a little bit more about discontinuous functions from the reals to the reals. So there's really only two types of discontinuities if I'm looking at a function from the reals to the reals. So there can't really be that many things that go wrong. The first type, it's the type that's kind of almost continuous. And that's what we saw in the last video. Here, I'll just scroll back up. This function here, it's sort of almost continuous. There is sort of a limit as I approach from the left. It's this value right here. There's a limit as I approach from the right. It's this value right here. They just don't match up with the function value that we have. So that's one type of discontinuity. And I'm going to call that kind of almost continuous. And the notation we have is if I approach from the left, so the limit as x approaches a from the left exists, and the limit as x approaches a from the right of f of x exists, but neither one but not both, sorry, but one of them isn't equal to f of a. Could be that both aren't equal to f of a, but at least one of them isn't equal to f of a. So this is also usually known as a jump discontinuity, because sort of if I come in from the left, I approach a value. If I come in from the right, I approach maybe a different value. Perhaps f of a is actually equal to this one, but not this one. Then I have a discontinuity, or a type 1 discontinuity. It's sort of almost continuous. This is left continuous. Since it's continuous from the left, it's not right continuous. That type of thing. Type 2, this is the more pathological one, and it's the type that's a little more difficult to work with. So I'm going to call this one very discontinuous. And what I mean by that is either as I approach a from the left or from the right, one of these two things doesn't actually exist as a limit. So I can't even think about what it would mean to be continuous in this case. So some examples, let's just do a simple example. Say f of x equals x if x is rational. I think we've seen this function before, and 0 if x is not rational. Then what it looks like is at all the rational points I have function values along the line y equals x. So it's a lot like this line right here, this dotted line right here. And at the irrational points, we'll go dark green with those. At the irrational points, I have 0. So let me get a bigger. So at the irrational points at 0, hopefully you guys can see these dots. Okay. Now this is discontinuous almost everywhere of type 2. There's one place where it's continuous, and that one place that it's continuous is at 0, right? Everything approaches 0 at 0. So from the left, I can say it's continuous at 0, and from the right I can say it's continuous at 0. But everywhere else, if I tried to pick a limit value, if I draw a circle around, say, this point, it doesn't contain any of the light green spots. And if I try to draw a circle around the light green spots up here, it misses the dark green spots. The only place where I can contain both the light green and the dark green is right at 0, and that's the only place that I have continuity. Okay. So this kind of looks like it's two different lines together, and everything seems fairly nice. It's bounded and all that, but there's even more pathological examples when I talk about type 2 discontinuities. I want to do one more example, and I need to prove a proposition before I sort of get into the meat of that example. So the proposition is if f mapping R to R is continuous at a point P, at a point X, then there is a neighborhood say in delta of X such that f of n delta of X, all of the outputs are bounded. So this as a set is bounded. It means all of the values in that set are finite, right? It can't go off to infinity inside that interval anywhere. And these are open intervals, which makes it a little bit stronger in some sense. So let's prove this. Okay. So we're going to use continuity, so let epsilon be bigger than 0. Then there exists, that's a logic symbol for there exists, so let me write out there exists. Then there exists delta bigger than 0 with f of n delta of X contained in epsilon of f of X, right? That's our definition of continuity. This doesn't quite look like our metric space definition of continuity, but what this says is if I take anything inside this neighborhood, it fits inside the epsilon neighborhood. So if I take something close to X and I hit it with f, it's going to be close to f of X. That's continuity. And since these are in the reals, this equals f of X minus epsilon, open, to f of X plus epsilon, which is bounded. By f of X plus epsilon above and f of X minus epsilon below. Okay, and that's what we needed to prove, right? I found this delta that bounded f of n of X, and f of n sub delta of x. Okay. Alright. What I'm going to show you is a function that's discontinuous everywhere and in fact unbounded everywhere. So it's like extremely discontinuous. It's a very pathological function. Okay. So when we were talking about continuity in the book, I had you look at chapter 4, number 18, and it had this function that I kind of called the yardstick function or the ruler function. And let me kind of recreate that here. So let x be a rational number, and for sake of notation we're going to say x equals m over n, where this is reduced. It is sort of simplified as far as possible. I have made there be no common factors in m and n. i.e. the GCD of m and n equals 1. So I can't take out any other factors from the numerator and the denominator. Okay. Then define f of x to be, well, we're going to kind of do the same thing. We're going to split off the rationals and we're going to split off the irrationals. We're going to say it's going to be 0 if x is not in Q, and n, how big the denominator is, if x equals m over n in Q in lowest terms. Okay, this isn't quite the same as the ruler function from question 18. What the ruler function did was, so question 18, this line was 1 over n. We're going to make it n, so it gets really big. If you make it 1 over n, this function's continuous almost everywhere. Right? Everything kind of goes to 0 as you get close to irrational numbers. To get closer and closer to that irrational number, you had to make your denominators bigger and bigger. So that would make it continuous at the irrationals and discontinuous with jump discontinuities at the rationals. But we're going to do this instead, and instead of getting closer and closer to 0, these things get closer and closer to infinity at the irrationals, and they stay finite at the rationals, but being finite at the rationals and kind of infinite almost everywhere else, and 0 on the irrationals, it makes for a really messy function. Okay, so I'm going to prove this function is unbounded on every interval. No matter how small you make the interval, you get an unbounded function. You get values that get bigger than any number that you can think of. So let's let m be a possible bound. For the interval, say a, b. All right. We want to get something bigger than m, and we want some rationals that are inside a and b that are bigger in denominator than m, so that this function is bigger than this possible bound. So let b minus a over 2 be, we'll call it epsilon. Then there exists n such that epsilon times n is bigger than 1, and n is bigger than m, and n is prime. There's an infinite number of primes. There's an infinite number of numbers. So I can just take a really, really big prime, a prime that's bigger than capital M, and a prime that takes me out farther than 1 over epsilon. And we're going to use this number to find some rational numbers between A and B. Okay, so then there's an M such that A is less than M over N is less than M plus 1 over N is less than B. Okay, I needed both of these in here. That's why I had to divide the interval by 2. I need both of these in here because maybe M and N weren't relatively prime, but one of these two numbers, maybe this number or this number, one of the two is going to be and reduced because N is prime. If M is a multiple of N, M plus 1 is not a multiple of N. And if M plus 1 is a multiple of N, then M itself is not a multiple of N. So one of these two is reduced. So either, and maybe both of them are in lowest terms, but either f of M over N equals N, or f of M plus 1 over N equals N. And both of these, or one of them, so M being smaller than N, is not a bound for f on AB. Since M was arbitrary, I can find infinitely large values of f on this interval, so that it's completely unbounded on that interval. Since it's completely unbounded on that interval, since it's completely unbounded on every interval, there's no way that I can make any point a continuous point for this function. So no point x has f of x continuous. Say no point P has f of s continuous at P. And these are terrible discontinuities, right? There's no limit whatsoever, because if there was a limit, it'd have to be infinite, and infinity is, well, it diverges to infinity if anything, but it can't do that. So this is a very pathological function. Okay, those are the two types of discontinuities, and we're going to start talking about differentiation now.